Okay, so this is presentation of the basics of small angle neutron scattering. Go over the outline, the sense technique, introduce it, then sense data analysis like standard plots, the Guinea plot, Perrault plot, sense models, and then inverse Fourier transform. This is something about shape reconstruction method. Cover two sense research topics, sense transitions in pluronic P85 and clustering in PEO water solutions. Final points describe statistics about the sense user program at NIST, then briefly describe two other instruments, the U-Sense instrument, ultra small angle, and the V-Sense instrument, which is under construction at NIST, very small. Okay, the sense technique. This is the NIST old guide hall. We see the two 30-meter SANS instruments as of last year. It's a very busy place, lots of research, exciting science coming out with a healthy user program. The NIST new guide hall. So we see one of the two 30-meter SANS instruments got moved to the new guide hall last year. There's a 10-meter SANS as well, still being constructed, some instruments not finished yet. Okay, small angle neutron scattering. The method involves 4 steps: monochromation using a velociselector. Velociselector is a cylindrical drum with a helical slot carved into it that spins at very high speeds, like 5,000 RPM. Remember that neutrons are not photons. They don't travel at speed of light, finite speeds, like 5 angstrom neutrons that we use here travel at about 800 meters per second. Then collimation using 2 apertures, source aperture and sample aperture, scattering. Here we have a number of sample environments, and then neutron detection using area detector. The scattering variable is inversely proportional to the neutron wavelength and proportional to the scattering angle. Remember, this figure is not to scale. The instrument is about 30 meters long, but the detector is about 64 centimeters in size. Nanoscale structures, type of science that's performed using small angle neutron scattering. This is the scattering variable. This is the d-spacing of the sample. In other words, real space, reciprocal space. Lots of polymer research, exciting, still a strong component. Complex fluids or self-assembling systems. Biology. Now a third, and the rest of all of the other science, the last third. I mean, more like a fourth, last science, everything else. So this is small angle neutron scattering, about 3 orders of magnitude in Q in scattering variable, and the U-Sense instrument, about 2 orders of magnitude, takes us down to d-spacings of 20 microns. So sense cross-section. The scattering intensity has 2 contributions. One is called coherent. It's Q-dependent. It's proportional to the contrast factor. It has information about the structure. And one is independent of Q, is called incoherent, scattering mostly from hydrogen atoms. There's no information about structure, just the density of the sample. The coherent part is a signal. The incoherent part is the noise. We want to minimize noise, maximize signal. In other words, we want to minimize the amount of hydrogen in the sample. So the contrast factor involves the scattering length densities. It's just like the scattering length per unit volume for a monomer or a micelle or whatever. The contrast match method. So this is deuteration is a form of changing contrast, changing hydrogen atoms by deuterium atoms. This finite contrast. If you have, for example, a solvent, same deuteration level as your particles, you will not see anything, 0 contrast. Multiple contrast, if you have different contrast for different particles. And then contrast match 1, you'll see only 1 particle. Sense data analysis, standard plots, I'll cover Guinea plot and Perot plot, SANS models. We have about over 100 models that we have developed in our SANS data analysis package, inverse Fourier transform, shape reconstruction. Just one slide for these two. Guinea plot, Guinea Perot regions. So we're showing here a calculated form factor for a cylinder with a certain length and a certain cross section. So here we see the low Q Guinea region. So this is low Q where the window of the instrument is bigger than the rod itself. So if we take what is called the Guinea plot, log of the intensity versus Q squared, log of the form factor versus Q squared, the slope is proportional to the overall size of the radius. This is called radius of gyration. So now in this intermediate Q range, goes like 1 over scattering variable to the first power because it's cylinder, 1D, and we don't see the entire cylinder, but we see only the cross section. If we do what is called a modified Guinea plot, log of Q times P versus Q squared, the slope gives us the cross-sectional radius. Now at high Q, it drops like 1 over Q4. This is called the Perot law in the Perot region, and we're seeing only the surface of the rod, of the cylinder. In other words, we can know whether it's rough or smooth. SANS models. SANS scattering involves either macromolecules or particles. In each case, we have what is called a single macromolecule, single particle form factor, and an intermacromolecule or interparticle structure factor, P of Q and S of Q. So the cross section, which is really the scattering intensity, is proportional to the volume fraction of the macromolecular particles, to the contrast factor, there it is again, to the particle volume or macromolecular volume, to the form factor. So these form factors are not hard to model, it's just geometry. But structure factors are harder to model. But we got really lucky in the sense that for macromolecules, there's what is called random phase approximation to model a structure factor for polymers in the homogeneous phase region. And when we are scattering for particles like micelles or proteins, we have what is called the Ornstein-Zernike equation, which allows us to model the structure factor in various conditions. So here it is, the Ornstein-Zernike equation. So let's assume that we have compact spherical particles. The form factor is P of Q. The interparticle will be the structure factor S of Q. So there are analytical solutions for these types of interaction potentials, like hard sphere interaction potential, or screened Coulomb when the particles are charged, like micellar charged micellar systems, or a square well for sticky spheres. So we're showing here the hard sphere potential. This is the form factor P of Q. This is the structure factor S of Q. There you go. First coordination shell and so on. The product of the two is the green one as a peak. That's structure factor peak, and then it dies out. It dies out pretty quickly, but has wiggles which get smeared out by polydispersity and instrumental resolution, but goes down like 1 over Q4. That's the Perot law, the envelope. Okay? So let's say something about Fourier transform. Microscopy methods make measurements in direct space. In other words, we see an image, we're looking at the density of the object, like optical microscopy or electron microscopy or something. But scattering methods do make measurements of the density correlation function. I'll explain. This is the single particle form factor. It's proportional to the density correlation in reciprocal space, in Q space. And there's what is called the Fourier transform, just simple mathematical transformation. Okay? The Fourier transform involves this integration over volume in real space, and this sine QR over QR, R squared P of R. So P of Q, the form factor in Q space, and P of R, it's Fourier transform in real space. This is the density-density correlation function. I'll explain. If we have a sphere, we pick out a point inside randomly, and we look around us. At a distance r, we either find scatterers, a second scatterer, or not find a second scatterer. So if it's inside, the probability will be equal to 1. We find a scatterer. If it's outside, it's equal to 0. There's no scatterer at a distance r. Okay? So mathematically, we can work out this probability. It's called the radial pair correlation function. There it is. We can plot it. It has to go to 1 for r equals 0. I mean, if you're very close, you're sure you will find another scatterer. It has to go to 0 for r equal 2. If you're really far away, then everything has died out. But remember, what is involved is not P of r, the blue curve, but r squared P of r. Let's plot r squared P of r in red here. There you go. So this is really interesting because this r squared P of r has a peak at the distance r. So in other words, you have a globular object, you do the inverse Fourier transform, you find a peak. That peak position is giving you the average radius of this globular object. Interesting method. Shape reconstruction and inverse Fourier transform. Here I'll just flash an example. These are peptide hydrogels that form fibers. These are the cross section of the fibers. Here, using the shape reconstruction method, this is the Svergen program, and this is the inverse Fourier transform. We get these peaks, and the results for the two methods correlate. I mean, this is really involved. Only a couple groups use this shape reconstruction method, but the inverse Fourier transform, many people use it. Okay? So, science research topics, we said 2 topics. Phase transitions in pluronic PAD5 solutions and clustering in PEO solutions. Okay, here we go. The first topic, pluronics. Pluronics are tri-block copolymers with polypropylene oxide at the center and polyethylene oxide at the end. Remember that these two, ethylene oxide and propylene oxide, dissolve in water at low temperatures, but this one doesn't dissolve in water at ambient and high temperatures because too many carbons. We looked at PAD5, which has this number of monomers for each tri-block copolymer. This is at low temperature. At high temperature, it forms micelles where the PPO is inside and the PEO is still dissolved outside. Okay. Pluronic micelles, let me show you sense data right off. We took very low concentration so that we don't have to deal with structure factors to start out with. And we measured for a range of temperatures. Low Q, 10 degrees C, we see 1 over Q to the 5/3. That's unimers, dissolved polymers. Okay? When we went to 50 degrees C, the black curve, we see 1 over Q to the 0, 1 over Q4. Aha. This is the Perrault law. These are compact objects. They're spherical micelles. Okay? At 70 degrees C, we get 1 over Q1, 1 over Q4. Remember, these are cylinders, 1 over Q1. Cylindrical micelles. When we heat up even more, 90 degrees C, we get 1 over Q squared and kind of 1 over Q4. These are lamellar micelles. Very interesting. I mean, you can map out all of these phases just based on observation. Okay? I mean, the last phase here, the last data set 100 degrees C, very close to the boiling temperature of water. Here we're using deuterated water, was at 101.4 degrees C. This is very close. This is inside the pressure cell that doesn't boil off. And we were able to observe a new phase here. We got lucky. Okay, phase diagram. I of Q at low Q versus temperature. You see these plateau regions, spherical, cylindrical, lamellar micelles, and so on. So if you have many samples and you do SANS, you can map out the phase diagram. That's the volume fraction, temperature. These are the various phases. Okay, so here we use the model to fit the data. This is the form factor. This is the structure factor. For the form factor for spherical particles, this is the so-called Bessel function, spherical Bessel function, first order. And here we used hard-sphere interaction, so-called Perkusiewicz closure. Okay, so we have the scattering intensity, and we do the fitting for 10% P85 Pluronic, for example. So 10%, we really need a structure factor. So we get the scattering land densities for the core, for the shell, and we fix that of heavy water, as well as the radii, the core and the shell. Okay, so we get a lot of information out. So core shell spherical particles. So if we go one step further, we use what is called the material balance equation. So the result for this sample at this temperature, we get something like 3000 PPO monomers in the core, a little bit of PO monomers, like 700 PO monomers inside. Each time you have PO, you have to hydrate it a little bit, about less than 1 water molecule per PO monomer. That was a surprise to find PO, which is highly hydrophilic, to find it in the hydrophobic core region. That was a surprise. But anyway, in the shale region, we find something like 3000 PO monomers, and here hydration is very, very plentiful. Lots of about 10 water molecules per PO monomer in the shale region. Okay, clustering in PO water solutions. There you go. The second topic. This is polyethylene oxide. This is ethylene. This is oxygen. So here we see the case of 5% PO in deuterated water. We see a low Q component and a high Q component. Fit to a simple model. The high Q component is just like Lorentzian behavior with a variable Poirot exponent, and there is a solvation intensity here. And we say something about the low Q clustering as well. Okay, so if we look at the solvation intensity, goes up with temperature for this molecular weight and so on. So which means that we're dealing with a lower critical solution temperature. Density increases with temperature. In other words, phase separation upon heating. So if you plot inverse of the solvation intensity versus inverse temperature in Kelvin, we get a straight line. That's mean field. Polymers are mean field. So if we extrapolate to the zero axis, gives a spinel temperature around 98 degrees C. It's for polyethylene oxide, deuterated water for this molecular weight. Miscibility phase diagram. So using many volume fractions, one can map out the phase diagram, or you get the one phase region, the completely mixed, and the demixed phase, the two phase region. We get the lower critical solution temperature here, and so on. Polymer demixing transitions. It's almost a crash course on mixing, demixing in polymers. So if you if you phase separate upon heating, there's a lower critical solution temperature. One phase, two phase, and so on. LCST. If you phase separate upon cooling, there's upper critical solution temperature. And one phase, two phase, and so on. UCST. Okay? These are the two main cases we'll deal with here. So we said LCST. It's called the spinodal line. This is called the spinodal region. This is called the binodal line. Could be obtained using light scattering. This one is small angle neutron scattering. The region in between is called the nucleation growth region. And this is the critical point. Okay. Clustering. Second topic. So let's get back to the same science data. We dealt with salvation. Let's deal with clustering now. Assume just a power law with a periodic exponent at low Q. We see it's going up. We don't see it level off, but there is a tail. So we saw that solvation intensity increases with temperature. The clustering factor decreases with intensity. Completely opposite. That's strange. Let's try to understand what's going on. Okay? Let's go to the Flory-Huggins interaction parameter. So we said LCST, phase separation upon heating, the so-called Flory-Huggins interaction parameter, decreases with inverse temperature. In other words, when you increase temperature, the parameter increases to get you to the two-phase region. So the other case, phase separation upon cooling, we see that the Flory-Huggins interaction parameter, when you cool down, gets weaker and weaker. It gets you to the one-phase region, mixed phase region. Okay, so this is Flory-Huggins parameter for LCST and UCST. Okay, so let's look at, for example, ethylene oxide monomer and D2O. Let's assume that ethylene oxide is a diblock copolymer. In other words, we'll be dealing with three Flory-Huggins interaction parameters: ethylene oxygen, ethylene water, and oxygen water. So we talked about the RPA. The RPA gives us the structure factor for diblock copolymer mixed in solution and so on. So we just turn the crank and feed the data, and these are the interaction parameters we obtain. The three interaction: ethylene oxide, ethylene water, oxygen water, and oxygen ethylene. Lo and behold, these two are LCST, ethylene in water and oxygen in water, but the third one turns out to be UCST. In other words, phase separation upon heating for these two, but upon cooling for the third one. Things are getting a little clearer. In other words, this clustering occurs at low temperature. The PEO in water is a frustrated system. What happens is the ethylene part do not like the oxygen atoms at low temperature. There is nothing they can do about it, but they're covalently bonded to it. So what happens is they like to associate with other ethylene ethylene groups when they can, so they stick. When two ethylene groups come close, they just stick and give you this clustering at low temperature. It's just like a frustrated system. Okay, clustering occurs a lot. Is the gunk at low Q takeoff. Case of polyelectrolytes, polyacyric acid, deuterated water here. Synthetic polymers, we just saw PEO in water. Biomacromolecules like DNA in water, as well as biopolymers. They all have this low Q gunk. Most water-soluble stuff have the low Q clustering due to the frustration interactions. The hydrophilic and the hydrophobic. Mostly hydrophobes are not happy, they stick together to give you large networks. Those are the clusters. Okay, final points. The science program at NIST. There are two 30-meter size instruments, Center for High Resolution Neutron Scattering, one 10-meter size NSOFT industrial consortium. Get beam time through beam time proposals or requests. Science program gets about 200 experiments per year, resulting in some 80 publications per year. There's the website, cnr.nist.gov, programs, science. Upgrade and vScience. So this is the reactor. This is the old guide hall. This is the new guide hall, the 230-meter science. There is also 40-meter vScience under construction, and a U SANS, which is a thermal instrument. Let me say something about these two instruments. Let me show you SANS here from a worm like micelle. There's the SANS 3 orders magnitude. There's the U SANS, very low Q, down to 20 micron in size, despacing. The V SANS, which is under construction, will overlap with these two and give us something like 1, 2, 3, almost 4 orders of magnitude. Online references, webpage, SANS Toolbox. There's a 1-week summer school every other year, small language on scattering. There's a 3 credit hour distance learning, and thank you.